Really, in the beginning, we wanted to be pretty micro. And as we got into the economics of like a 1 to 2 megawatt reactor, it was not very attractive. So, in us making that jump, and we started with a 2 megawatt design. Going from 2 megawatts to 10 megawatts just made all the sense in the world. We definitely want to be a microreactor because we think the use cases are very broad and there is incredible demand for something like this at this size. But the economics are the most important thing at the end of the day. So if it's not economical, we're not going to be able to commercialize. And that's why we made the jump. The nuclear industry always bigger is better, but I think we're really going to try to push for like the biggest microreactor that we can.
A warm welcome back to Decouple. Today I'm joined by Samuel Gibson. Samuel is a serial entrepreneur, mechanical engineer, and engineering leadership graduate from the University of Nebraska-Lincoln. He is the 25-year-old founder and CEO of Hadron Energy, a micromodular reactor startup, on the verge of a pretty major $1.2 billion business combination with the special purpose acquisition company Gig Capital 7. Sam, did I get that all correct? 25, 24?
24, yeah.
Oh my God. Oh my God. All right. Cool. So listen, it's great having you on the show. I have some opinions about microreactors, but I'm always up to sort of challenging my biases. And so I'm really interested in hearing from you, getting the story of Hadron and this pretty extraordinary business combination with Gig Capital 7. Obviously, AI is hot and energy is hot. Nuclear energy is very hot right now. We've seen some pretty eye-watering market caps out of Oklo, NuScale. I mean, things are bouncing around a little bit, but it is a good time to be in the startup space, it seems. So first off, just tell us a little bit more about yourself. Then let's talk about Hadron, and then let's talk about this. I don't even see. I'm like fairly ignorant in the investment space. I was going to call it a SPAC, but I think it's a business.
Yeah.
Is it the
That's
term
right.
is SPAC? All right, we'll get into what that is in more depth in a bit. But first, give us a little more of your background.
Of course. Well, thank you so much, Chris. It's a pleasure to be here. And yeah, I'm Sam Gibson, the founder and CEO of Hadron Energy. This is the second startup I've been a part of. So I really brought, some great perspective the second time around, given starting a company is definitely not easy, but it's something I was very passionate about. And I was even more passionate about microreactors, small modular reactors. And ultimately, what I did was when I was at the University of Nebraska, I took a very deep dive into everything nuclear power, and I examined all the different types of cooling, light water, liquid sodium, helium gas, and I feel the quickest way to the market is through a light water design. Specifically, we are a integral pressurized water reactor. With that being said, what I did was a pretty in-depth analysis of other types of companies, and I was honestly surprised that there wasn't a single licensed microreactor out there in the US. And I thought this was a major problem because I think these things have the potential to seriously create a big impact. And it was a big enough problem that I thought we could get some very ambitious people behind it, which at this stage we definitely have. We have over 150 years of experience in the nuclear industry on our team. We continue to hire some outstanding engineers. Most recently, Olivia Hand, for example, she's our head of reactor design from TerraPower. So we're starting to get some excellent people on the team.
I saw you brought on Ross Ridenour as well, former CNO at San Onofre, a big role in the UAE on the Baraka reactors. Interesting character. Yeah. I love his forgotten reactor posts on LinkedIn. So you're building quite the team.
Absolutely, and that's obviously, as you know, the most important thing in any company really is the quality of the team, and we just have very high standards. And yeah, Ross and, for example, Andrea Vale, she's our head of reactor licensing, worked at the Nuclear Regulatory Commission for over 30 years. With that being said, yeah, we've got some excellent experience, but we're also doing something completely novel. We've got a pretty amazing novel core design, and this primarily came from Andrew Ward, our CTO, as well as Benoit Forget. He's an advisor to us leading the reactor physics effort. He's also the department chair at MIT for nuclear science and engineering.
So, Sam, just help me understand this again. You're 24. Like, how do you assemble the dream team? You must have some capital flowing in already. I'm not sure what you can disclose,
Mhm.
but yeah, like, how do you get to this position of hiring this caliber of people? And again, this would probably be a jumping off point to talk about the SPAC. Um,
Mhm.
but demystify to the ability that you have. How you get here at 24 doesn't really compute for me.
Yeah, it's a great point. And to be fair, and maybe this might sound a little weird, but I'm just a workaholic. At the end of the day, I love what I do. And I think if you really are passionate about something, you'll put everything behind it that you can. And this is the age for me that I believe I can really push incredibly hard to seriously make something happen. With that being said, it kind of traces back to my university days of getting connected with some amazing people. As you mentioned, I went to the University of Nebraska Lincoln. I was very involved with the American Society of Mechanical Engineers, ASME. I ended up winning two global engineering awards through this organization, and ultimately, this really expanded my network. So I was very involved with ASME. I started meeting very top engineers, and this was just in college as well. So I think I'm just very competitive, and I would love to make a difference. And I think this company truly is positioned to make a pretty positive impact.
How'd you get a letter from the president?
That's a great question. Part of my ASME efforts, I met a gentleman named Mahantesh Hiremath, who is an advisor to me, and he has some excellent connections in the DC area. And we just wrote, the White House a letter saying, "Hey, this is our mission. This is what we're doing." And this is what they sent us back. They said, "Hey, we fully support what you're doing." It's really exciting to see. And actually, that note came in the mail the same day we announced our SPAC, which was probably one of the most crazy days of my life, easily. So it's pretty amazing.
Okay, so what's a SPAC? I'm aware of Sam Altman's Alt-C Acquisition Corp that took Oklo public. I think I'm not sure if that was like 850 million. I think it got them about 500 million in gross proceeds or
Mhm.
proceeds. So what's the story there? How does this work?
Yeah, it's a great question. So really what a SPAC is, it's a special purpose acquisition company. So it's a vehicle that, as you mentioned earlier, it's a blank check company, which means, for example, Gig Capital 7, who we're working with, and this is all like in the S4 that we've just filed as well with the SEC. They have approximately $200 million in their trust account. And we're also going to raise, some capital on top of this. But basically what this is it's a merger with, and their target, by the way, is to really work with deep tech, like high tech companies to finance them to be able to commercialize and become a publicly traded company. So as you mentioned earlier, the timing right now is excellent for this industry, and I think we really need to capture the momentum with actual progress. So that's why we went through with the SPAC. Is the least dilutive in terms of the cost of capital. In terms of raising private capital, this is a far better route.
So just so I understand it, like Gig Capital 7 is basically like a pot of money looking for an opportunity, a company to merge with, and it's a really quick way to go public. And then I guess retail investors can pile in on top of that, and you're looking around for other capital as well. But this is kind of a cheat code, I guess, to get launched. Sounds like.
In a sense, it's a streamlined way over the traditional IPO route. And I think that's important because SPACs enable companies that maybe couldn't hit the necessary requirements of a traditional IPO. Traditional IPOs take far too long. I think, they're pretty expensive. There's a whole process to it. If you're a very established and mature company, that's probably the way to go. But in a company like Hadron, where it's very capital intensive, of course,
Yeah.
we're going to have to start, building hardware very, very soon. So the influx of capital is really what's going to unlock our next phase of growth.
I just trying to understand like the scale of that capital. Like I have a few comparators. The Tesla Model 3 apparently took about $1 billion in terms of design and engineering and prototyping. That's an EV, like way less moving
Right.
parts than an ICE vehicle, let alone a nuclear power plant, way less regulated. What is it? NuScale, I think, also an integral pressurized water reactor, a little bigger than yours. 500 million for their NRC certification. Hopefully, having gone through the NRC has, learned some lessons there. And for another company coming with an integral pressurized water reactor, that can be cheaper. But developing a nuclear technology, prototyping it, qualifying the fuel, certifying the design, developing prototypes, like this ain't cheap. So maybe walk me through a little bit how you anticipate that unfolding, and as much as possible, put some kind of dollar amounts there so we have a sense of. And again, is it 200 million you sort of anticipate that you'll have as an operating budget? What is the 1.2 billion?
Yes, the 1.2 billion is the valuation itself. As you likely know, you raise capital, and then the valuation can be higher than dollar for
The
dollar,
float. Okay.
basically.
Yeah.
But really, what this is all about for us, we're targeting a little bit over 300 million in net proceeds. We do believe, by the way, that since we're leveraging low enriched uranium plus LU plus and mostly off the shelf components wherever we can, that we actually have a very good handle on what this reactor will cost. So in the meantime, we've been trying to get as many quotes from vendors, whether manufacturing or, as you're saying, fuel. And knowing this, I think we do have a pretty good handle. I think this will fluctuate, based on the timing of when we buy everything. But based on what we're seeing, we have the reason to believe the first reactor will cost about 100 million,
Okay.
which is interesting, obviously, compared to the other types of reactors, given historically they're expensive, right? Far more expensive than that. But based on what we're seeing today, this is what our estimate is so far.
Okay. I think that number's gone up since I was watching some other interviews and you were hoping for 50 million. It seems like the more you get into this game, the deeper you go in, prices go up. And we certainly saw that with NuScale, but that would be about 10,000 a kilowatt. I think NuScale, their initial estimate was, oh man, I might be blanking on this, but they ended up around 20,000 a kilowatt, which led to UAMPS, unfortunately dropping the carbon-free power project. I guess again, in terms of like, I probably can't get too granular, but just thinking beyond the cost of the first unit, what do you anticipate the cost of working through the NRC to be? Or I know you're using LEU plus, and I think they've loaded some LEU plus into Vogtle recently, but I think you guys want to keep it in the reactor for 10 years, and there's going to be a bunch of corrosion issues and fission gas buildup and things like that. So there's a lot of steps. And in this podcast, where we have the luxury of being able to get a little granular. So interested again if you can walk us through some of those steps and what the anticipated costs will be.
Yeah, of course. So the first note on the $50 million estimate, this was for a non-nuclear prototype. But ever since then, we've actually shifted away from that strategy, and we're focused on building a one-to-one scale for the first unit. So that's why it basically doubled in price.
That will be not just a non-nuclear prototype, an actual commercial product?
Yeah,
okay.
that's right. This is our target right now.
Yeah.
And as far as the fuel qualification, as you know, the U.S. government was shut down for a little while. We actually had a fuel qualification meeting set up with the NRC many weeks ago, but then the shutdown kind of canceled that one. So we rescheduled it coming up here. So that's obviously a topic we're going to discuss, and that'll, have an impact on our fuel strategy. But it's definitely interesting with approximately 8% enrichment. The 10-year refueling cycle is actually very attainable, but this is something we're constantly iterating on, and obviously depends on what the NRC comes back with.
Right. A lot of moving parts.
Yeah.
Yeah, integral pressurized water reactor is definitely one of my favorites. I've become really interested in the what I'll call the world's only serial produced SMR, which is the Russian icebreaker reactor, the RITM 200. It's on icebreakers. They're starting to get units built to go on floating nuclear power plants, and they have some land-based versions. So I definitely want to kind of get into the weeds there in terms of some comparisons. But in the U.S., never built, but there have been integral pressurized water reactors. I should say there was one. I'm not sure if the U.S. built it. Babcock and Wilcox, the reactor for the Otto Hahn, basically the West German version of the UN Savannah ship. But we do have mPower. They attempted to get a integral pressurized water reactor across the line. NuScale is obviously still in that process. The early preconceptual work on NuScale began in the year 2000. The company launches in 2007. It's 2025. It's been a long time, right? mPower, I guess just couldn't find a customer. So like what's different about Hadron in terms of being able to get around those challenges with what I agree is a promising technology in terms of staying fairly conservative with well understood pressurized water reactor technology?
Oh, this is a great question, and honestly, I like the saying, "The second mouse gets the cheese." We feel as if NuScale, really did lay the groundwork as far as the licensing trajectory. So we have a lot of material that obviously is publicly available that we can reference and say, hey, this is how we can help, facilitate our applications. But I know you brought up earlier a point on what do we expect like the regulator to cost. I don't know if you saw, but the NRC recently reduced their rates. I think it's around $180 an hour versus $300 an hour.
Okay.
And there's also, I don't know if this is exactly firm yet, but there was talks at the NRC of capping 1% cost of the reactor. Like that's the maximum cost that licensing can charge. So you have a $100 million plant, $1 million to license. So that's something that they have been talking about. So of course we're staying at the forefront of all this. But to answer your question on how we feel about commercializing this, our whole strategy, as I mentioned, is how do we leverage existing knowledge, technology, off-the-shelf components? Because what we're seeing in the industry is too many players are trying to custom fabricate like everything. They're using exotic coolants, exotic fuels. That's just not, I don't think that's the best way to actually get to the market.
But I mean, you also said there are no microreactors right now. This is a niche to step into.
That's right.
Like off the shelf, I mean, we're in the kind of living through the atrophy of the once glorious U.S. nuclear sector, right? I mean, we've got Watts Bar that took something like 42 years to come online. There was a pause. Vogtle units 3 and 4. Is there much like waiting around on the shelf for nuclear in general and for microreactors in particular?
No, it's actually a really great question. I mean, I think generally when I'm thinking about this, I'm referencing probably the fuel. Especially when you compare ourselves against other advanced reactors.
Yeah.
More so off the shelf fuel than anything, because the fuel qualification for TRICell, for example, it's just going to take a while. But of course, I hope it's successful. But we have to custom fabricate our reactor pressure vessel, heat exchanger, steam turbine, all this stuff. So yeah, there is still definitely going to be custom components, but wherever we can, we're going to try to leverage off the shelf. So we're actively working on this right now.
We interrupt your regular programming for an appeal from our sponsors. That means you, hopefully. Decouple runs on a strange fuel mix. World-class guest experts and a talented editorial and production team. One of these is not free. If you want more long-form, numerate, and historically informed exploration of nuclear energy, geopolitics, and climate change, you can help in a few very concrete ways. Upgrade to a paid subscription. Join us on Substack, and think of this as buying a small equity stake in independent nuclear journalism. You can also make a tax-deductible donation on our website through our fiscal sponsor. You can find the button again on our Substack site. If you are a utility, a vendor, fund manager, or policy type who reads this work, support it like you would any other research product. If Decouple informs your decisions, help fund the next episode that saves you from a bad one. If you value having at least one outlet that treats nuclear as an engineering and industrial project, not as vibes-based asset class, please consider paying for it. Financial independence is what guarantees editorial independence, and it is what makes Decouple so special. Thanks again for listening to this message. Now back to the regular programming. Let's just take a step back and again get a better sense of the design. I think it has evolved, as you're saying. It's fluid. You've got, you've hired great people to start getting towards eventually that coveted NRC design certification. You guys started like truly micro, like one megawatt. You're up to 10 megawatts. Why the jump, first off, and secondly, I'll answer that, and then we'll get into just describing the overall vision in terms of what the plant looks like.
Yeah, of course. So really in the beginning, we wanted to be pretty micro. And as we got into the economics of like a 1 to 2 megawatt reactor, it was not very attractive. So in us making that jump, and we started with a 2 megawatt design, going from 2 megawatts to 10 megawatts just made all the sense in the world. We definitely want to be a microreactor because we think the use cases are very broad and there is incredible demand for something like this at this size. But, the economics are the most important thing at the end of the day. So if it's not economical, we're not going to be able to commercialize. And that's why we made the jump. The nuclear industry always bigger is better. But I think we're really going to try to push for like the biggest microreactor that we can, in a sense. And it's interesting, like there's different definitions for microreactor. The NRC doesn't really define the specified range. They just say, well, special nuclear material limit. And they, that's basically what they say. The Department of Energy says microreactors are 1 to 20 megawatts electric. SMR is 20 to 300 megawatts, full scale 300 megawatts plus.
So it's always kind of shifting sands in terms of those definitions. Okay, so you scaled up for economics. I think I was running some numbers like at 100% capacity factor, like $150 a megawatt hour, like 2 megawatts gives you like, I think 2.6 million a year to pay your full-time equivalent staff and take care of your cost of capital and your OpEx and your fuel. So obviously that's pretty challenging. Now you're up at about like 13 million. Assume again,
exactly.
Hopefully the hyperscalers are willing to pay that high premium of $150 a megawatt hour, but you have a little bit more wiggle room with 13 million. Still tight, it would seem to me, and that's why I kind of am a little skeptical of the micro size. I'm an economies of scale guy. But before we get more into that, let's chat again just about the overall vision as it is for what this reactor looks like. You mentioned it's an integral pressurized water reactor. Tell us more about again what this plant will look like. Is it going to be one reactor? Is it going to be a pod of reactors? You have I think probably the industry leading website.
Of course,
some great animations on there. So I've got some picture, but maybe we'll get the producer to throw up some images as you talk. But describe the concept. What does it look like?
Of course. So generally speaking, we really want to have multiple modules in one like containment building, and they can actually share a common suppression pool, for example. What we're looking to do, and by the way, we do have hyperscalers that are interested. So when you're talking about the 15 cents per kilowatt hour, the interesting thing is they'll say, hey, it's on the higher end, but we're still willing to pay it. And if that's the case, then that's obviously a great, point for us to be. Obviously, demand is incredibly high. So if they want to continue expanding, they're going to have to pay. I mean, the supply is just not there right now. So they're kind of running out of options. But with this, then the second part of what you're mentioning, what the plant looks like. So on our website, as you're saying, we do have a very nice website. It shows you this common pool of multiple reactors sitting in this pool. And on the website, it has an air-cooled system. So we actually don't need external water. Multiple layers of safety, of course. And at the end of the day, the core damage frequency event, this is something that our engineers have actually went through and calculated based on, again, pretty well-known information. And they think we're basically at the phase of one core damage frequency event every 2 billion years of operation, which means it's an incredibly safe operation. And this is what our chief nuclear officer, Russ, right now, or has also put together. So we feel very great about this. And then, of course, you think about the operation of the reactor. Uh, you know, this is what people know how to operate, like water designs. So we feel pretty good about the full ecosystem. But I'd be curious to see what you think as far as like the economics as well.
Yeah, I mean, I think where my skepticism comes in is like the idea of micro is construction productivity is garbage. It's been getting worse, if anything, and the U.S. is just out of practice. China's eating our lunch in that regard. But if you get things into the factory, you can bang these things out. And when you look at an integral PWR, like again, I think that's a great choice because your steam generators are inside, your pressurizer's inside. It's a nice, tidy little package. There's still a bunch of balance of plant stuff you have to hook up, however, and the construction site doesn't disappear. I mean, just looking at the website and looking at any nuclear power plant, I think you guys are below grade.
Yeah.
Excavations, you have a suppression pool. It's not the size of NuScale's. I don't know how big it has to be for like 6 modules versus 1. I think you say 60,000 gallons, but that has to be seismic category 1. That gets really, really pricey. All that balance of plant stuff doesn't disappear, and I think there's MIT studies saying basically the NSSS, the shiny reactor part we all love to look at, and where the magic happens is like 1/3 of the cost. So how do you get around that issue? Like, can factory fabrication trump those fixed sort of construction costs, in your opinion?
Yeah, I mean, in my opinion, this is definitely like the strategy of a microreactor. Mass manufacturing, achieving nth of a kind. Obviously, the first of a kind is always like the hardest. Once you get this done, there's another like MIT study. I believe they say after 10 units, you can achieve pretty significant cost reductions, just in terms of manufacturing. So of course, I believe that with kind of serial production, you can see a lot of time saving and savings on cash, of course, when it comes to actually building these on the site. As much as we can, we're really trying to make it, in a sense, plug and play of, everything's prefabricated to the extent it can, except for the civil works and the suppression pool and all this stuff. But at the end of the day, that's, the microreactor strategy. How can we set up a gigafactory and make hundreds to thousands of these things so that we can reduce the costs very significantly? That's basically the strategy.
Yeah, it's interesting. As I said, I'm obsessed with an integral pressurized water reactor, the RITM 200. I will say it's the only SMR really out there at the moment. 8 units on icebreakers, and I think there's another 12 or 13 in production. The Russians are going gangbusters on this because, to open up the northern sea route, to open up the big copper deposits they have along eastern Siberia, gold mines, etc. They don't really have any other options. I will say nuclear's need to have, not nice to have technology, and it is need to have if you want to smash ice and dig copper in the middle of nowhere with 6 months of winter. That being said, like they're only delivering 2 to 3 units a year. That's what they're anticipating into about 2035. Some land-based units, I think it's going to be around 8 on 4 different floating power barges. And that's with, a design bureau, the OKBM Africantov. It's got like 4,000, engineers, thermohydraulic experts, neutronic experts, system integration experts. They've got like a 20,000 strong. I love these Russian terms, Atom Energomash. Their manufacturing division is massive. They have, 17,000 people in their fuel manufacturing. This isn't all going towards, this microreactor project, but it's part of a very healthy, robust ecosystem. And, as we've kind of mentioned, the U.S. is in a bit of trouble there. So as a startup, like if Russia making a pretty major like nation building effort, with a rationale, this makes sense. Like they don't have loads big enough for gigawatt reactors, obviously, so they've kind of come down to this 50 megawatt reactor. If as part of a nation building exercise, mobilizing, vertically integrated giant nuclear company only produces 2 to 3 units a year, how does a startup get to tens or hundreds? Like gigafactories sound great and they work for batteries, they work for EVs. We see that in China, but nuclear just seems different. So help me understand that.
I mean, yeah, this is exactly why we started Hadron. It's the $1 trillion problem. If you can mass manufacture reactors I think the opportunity is quite great. Obviously, it's a lot of work to get there. I think it takes a startup mentality rather than the government mentality. A lot of bureaucracy, moving slow. I mean, as you can see, we're moving pretty quickly. And I think the faster we go, hopefully we can, stand up a facility and start producing as quickly as we can. I think it really takes industry, to be totally honest, to actually make change because government, as I said, just moves very slow. So I'm very confident we can make well beyond 2 to 3 reactors a year. I think it's going to take a lot of work. It's also going to take a lot of capital, but I mean, this is what we're planning for, and yeah, we're looking at facilities right now, actually.
Outdo the Russians. That's always the goal. Um,
Yep.
so I think another concept that I find very interesting, and for me, this is sort of the I'd be interested in your opinion on this, but I think this is sort of the category error of the microreactor is essentially, it's a lot like a diesel generator, or at least that's what I think the category error is. And diesel generators, of course, scale from your 5 kilowatt, home diesel generator for if there's a blackout, your Generac, right up to, marine diesel engines that are like in the 50, 60, 70 megawatt range. And they can do so because it's like a block of metal, a bunch of moving parts. The inputs are like lubricating oils, diesel, air, exhaust. Maybe if it's a big one, there's some cooling involved. But it scales very nicely across those four orders of magnitude. Whereas nuclear comes with these gosh darn annoying issues of radiation and decay heat, which
Yep.
we had Nick Turan on a little while ago talking about microreactors, and Chicago Pile 2 was a 2 kilowatt reactor, but it still needed a meter plus of concrete shielding as a biologic shield to not fry people, right? And
Yeah.
so it's not that like it's a lower output reactor, so now you only need a foot of concrete. You still need that 5 feet of
Seen a
concrete
lot.
as your biologic shield. And then, there's just so many other things that factor into nuclear. Again, containment, biologic shield, these seismic category 1 civil works, all the regulatory hoops you got to jump through, the QA, licensing. I don't know if a diesel requires having like a crew of full-time 24/7 reactor operators, if you need a health physicist, if you need security. So like that's when I look at, some studies, I think Nordhaus, Yip, and Lovering, they have one about sort of cost reductions and learning in nuclear. And for me, I'm like, it doesn't really look like learning. It just looks like scaling effect. And our first CANDU was a 20 megawatt CANDU, but like the universal law of nuclear has been, accepting and thriving with these economies of scale. So how does Hadron break the mold on that?
Yeah, it's a great question. And in terms of radiation shielding, I mean, this is obviously a top concern for smaller reactors too. I had the chance to actually tour Berkeley facility, and I got to see how thick, the shielding has to be. It's pretty amazing. But, that's why we're having it obviously in a suppression pool. We have plenty of civil works as we've, shown in our depictions. So the shielding really shouldn't be a problem with how we're siting these reactors.
But it costs money. It costs a lot of money, right? Like that
Yeah.
steel, that rebar, the civil engineering, the excavation, the mud mat. Like, and it's like, I'm a doctor, right? But I've just nerded out on this, and like every layer that I learn about, I'm like, oh shit, there's another cost. There's another cost.
Yeah.
There's another cost, and that's what makes it daunting. But sorry to interrupt. Carry on.
If you look at like diesel generators versus a microreactor, and you try to run a diesel generator 24/7, they likely only last about 2 to 3 years if you're running them nonstop. And there's so many maintenance problems. The interesting thing is, of course, nuclear is expensive up front, and then it seems to be much better down the line. Whereas diesel, I think you start off pretty reasonable, and then you slowly increase your costs over time. So if you look at the full useful life, it depends on the situation. If you're looking at, I, for example, I actually talked with this military base. They have a whole fleet of diesel generators powering their facilities, and they consume 40,000 gallons of diesel every day.
Yeah.
And the logistics for this is just insane. So for me, like, of course, I'm a big proponent for decarbonization as well. So if we can decarbonize and like reduce all these logistics, in the long run, based on, again, I feel like maybe it's rudimentary estimates, but it seems to be reactors could be more cost effective in the very long run. Um, and so this is what I get excited about too, is comparing. You look at capacity factor, you look at everything, but most importantly, the decarbonization too. I think that's very important.
Yeah, no doubt, no doubt. I mean, again, another part of this, I think, we get fixated on the nuclear steam supply system because it's shiny and sexy, and the concrete and rebar is not. We also, with microreactors, get fixated on, and your website's got like a Cybertruck rolling up with
Yeah, yeah,
100-ton integral pressurized water reactor (RPV). But
yeah,
it's sexy when it shows up, but man, when you got to get rid of the thing or get rid of the fuel, and like I'm no nuclear waste phobe. We've managed it incredibly safely. Over the 70-year history of nuclear power, if we're just storing it, talking about civilian storage, not reprocessing and things like that, you can't find a single casualty associated with it. It's remarkable. But it gets more complicated when you have to divide those efforts, and maybe do them in a remote mine or a military base, when you have to store the spent fuel there, or potentially move it, and decommission it and things like that. Like this just, I think, also really follows scaling laws. If you have a gigawatt scale reactor and you're defueling your reactor every 18 months, you have an on-site spent fuel pool, you have dry cast storage set up, you have a permanent team that's ultra skilled in that. Like, just logistically, it all seems cheaper, and again, conforms to economies of scale. And again, like, maybe you can find a customer that's willing to pay, not just, 150 megawatt hour, but, 500. And you talk about really remote diesel operations, and they're getting up there, right? I mean, people are paying a dollar kilowatt hour.
exactly.
Talk about like that back end of the operations, and particularly, managing spent fuel in remote locations. Because, you talk about your reactor data centers, but also remote communities, military bases, maybe the
Right.
moon, right?
Yeah, yeah, and really what it comes down to for us, and this is something we've actually recently started looking at, is can we take the spent fuel and place it directly in dry cast storage? This is something that actually the engineers are finding could be a possibility, rather than going to a pool right away, for example, on the site. And this is something we're talking to the NRC about. Of course, you need a license everywhere you store fuel. So, the ideal situation is, it's mostly probably going to look like we store the fuel on site for 1 to 5 years, however long it is. Then you take it out, dry cast storage, and have it in a centralized facility. It seems to be that's the standard practice. But with this new sort of digging that we're doing, apparently this dry cast storage that we're looking at could potentially just take our fuel directly. So that's something that we're working on right now. But as far as like spent fuel management, as you're saying, this is something that's pretty well understood. It's something that we've been doing for a while. So I don't think there's anything too novel there for us. It's just going to come down to working with the regulator and figuring out sort of the best solution at the end of the day.
Yeah. Have you ever got to see, or like go and watch a defueling, or hang out in the primary fuel bay, or see them move casts around? It's pretty cool.
I haven't seen dry cast storage, but what I have seen, and I thought this was so fascinating, was I was at the Idaho National Lab and I got to walk across like a big pool of water. And at the very bottom, I think it was like 20 feet deep,
It's the
just a
yeah.
bunch of. Have you had the chance to check that out?
I've been very lucky. Yeah, I've been to a bunch of plants, and got to walk on the gantry over top of them as
Yeah.
they kind of shuffle. Not the reactor itself, because we're talking Candu is the one I was at, but in terms of the
Hmm.
primary fuel bay, they're moving things around. They're refurbishing, so they have to unload a whole ton of fuel before retubing all our reactors up here. So yeah, it's that Cherenkov glow is pretty unforgettable.
Exactly. It's really cool.
Yeah, yeah. I don't know how you solve that issue of moving fresh waste directly into dry cask. I mean, it would be screaming hot and melty and interesting.
It's interesting. I mean, this is again a discussion that's going on with our engineers, and you know, I I keep a very open mind. If they're saying that we're not, pushing the fuel as incredibly hard as it usually is, then maybe it comes out a little bit cooler. Again, this is something that we're working on, but um, from my perspective, it's probably going to look like spent fuel pool and then move it to dry cask storage.
Would you agree with or reject the characterization that Hadron's sort of like a mini NuScale? Because there's a lot of similarities, like multiple integral pressurized water reactors in a pool, which is, I think, your kind of final thermal sink. What else? I mean, those are the main things.
Yeah.
Smaller. Like, what's the difference? And again, like if NuScale's having trouble, like with UAMPS, and their costs have escalated, up to like $20,000 a kilowatt. Like, how do you differentiate yourself there? Is it that you're smaller? What's the difference?
Yeah. I mean, to be totally honest, I think really the costs jump pretty significantly from a microreactor to an SMR. The thing that I always found interesting was for like the operation of an SMR, you still are required to have a lot of the same full scale like requirements. And so you're essentially producing less power than a full scale plant, but you have similar costs. To me, that didn't make any sense. And I thought, well, what if we could just figure this out on the smaller scale, which of course I know goes against the industry of bigger is better, but I do think that there's a way.
What are some of those ways, though?
From my perspective, I think it's really important to have the serial manufacturing capability. I mean, if you look at the barrier to entry of building, uh, you know, SMR plant versus a micro, they're making it easier for micros than SMRs, I believe, especially going through the regulator. Um, we're seeing an accelerated pathways for microreactors. So this is what I think is what I mean. At the end of the day, all we're trying to do is find the most efficient way to actually hit the market with a reactor. So that's basically our model. Of however that looks like, that's what we're going to do.
I've heard this comparison, like we need to build airplanes, not airports, bandied about in terms of microreactors, right? And that the gigawatt scale plants are just, we look at trying to build airports in the West, and it's a gong show. So
Right.
if we could just build the airplanes, and that's where I think like that was the sort of NuScale model, and I think they're hoping to do their whole, integral pressurized water reactor in a factory, which does seem similar. And then they've got to do the civils, and their civils will be a bit larger than your civils, but they'll generate more revenue, just based on economies. I guess the problem is like when you actually look at NuScale, you're like, but you do need an airport, and that airport is this massive swimming pool that's again
Yeah.
seismic category 1, that's aircraft impact assessment compliant, and I think your plant is a smaller version, but I'm not seeing the fundamental difference there other than it being a bit smaller scale, which I guess you could say is going to help in construction, but it's also going to mean less revenue.
Yeah. I mean, from my perspective, and I think the assessment is fair. Like we feel again the optimized path to actually get to the market. That's basically our strategy. However, we can optimize the time to market. That's what we're going to do. Um, with this being said, yes, we have lower revenue, but we feel like we have more opportunities. I think the market is actually much larger for a 10 megawatt reactor, given the especially remote applications. There's a lot of remote applications in Canada. There's, you know, the ability for us to scale up 10 megawatts at a time. We can cover anywhere from 10 to, if we really wanted, and I asked a theoretical question to the NRC. I said, what's the limit? How many microreactors could I line up? And they said, in theory, infinite. So, I mean, it sounds really interesting, but
Like for a gigawatt scale data center, for instance.
yeah, but like obviously we probably wouldn't do that. I just think it's interesting.
Yeah. And I guess like some in terms of like the Bulls case here, it's pretty hard for these really big data centers to actually connect to the grid. There's a lot of politics there,
Yep.
right? Like Ma and Pa want their cheap electricity and don't want it all getting
Yeah.
sucked into AI generated porn or something like that. So in terms of that, trying to stay behind the meter, like what are some other sort of reasons why micro makes sense for some of these big loads like data centers? I think like a lot of your letters of intent are with data centers.
That's right. I mean, really, on-site energy and power, I think, is where the future is. You know, I think decentralizing energy as much as possible is very important because, you look at Texas, for example, they have sometimes very wide blackouts. Well, if you had all this redundancy of distributed energy, maybe that wouldn't be as big of a problem. It's just like an interesting case there. But at the end of the day, I think as as I was mentioning, a lot of applications need 10 megawatts or 20 megawatts, 50, and you can't put, like a new scale reactor that, just needs 10 megawatts, for example. I mean, the infrastructure that needs more utility scale. I mean, we're trying to have really that sweet spot of on-site generation as much as possible. And I think that's what's, pretty compelling to these data centers. So that, mom and pop does see an increase in their price.
Again, I totally love Ross's work with the forgotten reactors.
Yeah,
Like we've tried microreactors before, obviously, right? For the Army. Army's working on it again now with the Janus program, but the Army nuclear power program, we had like nukes under glaciers in Greenland, nukes on Antarctica, like Wyoming. What do you think some of the lessons are? That fizzled ultimately, right? So what are some of the lessons you think we can draw from the last microreactor renaissance in the like 60s and 70s?
Yeah, I mean, this is a great question. And at the end of the day, I think what we're doing is basically commercializing a Navy nuke at a, particular scale. But you look at these programs with the Army, we're going to be involved in Project Janus, preparing an application. I mean, I think it's something that just needs to be done, even though, to be fair, I'm not like an expert on the 60s and 70s.
Yeah.
I was born a little bit after that, but
Talk to Ross. Talk
you
to
know,
Ross.
yeah,
He'll fill you
he'll
in.
know. you know,
Yeah.
so I think he'll obviously have a great perspective, and yeah, he's really excited about this reactor, and at some point, definitely be worth a conversation with him.
I've actually reached out to him. I'd love to have him on at some point. So in terms of like your role, like you're like you're the CEO. You're kind of a convener. Like you have a mechanical engineering degree. I imagine you did some nuclear engineering courses as part of that. But you kind of rely on a team. So again, I just want to get back to this phenomenon of like a 24-year-old running a company that might have a
Yeah,
1.2 billion dollar valuation, and
of course.
I guess how you kind of juggle that because you're early in your career, you're surrounding yourself with good people. I don't know any like organizational insights from the CEO's chair there.
Yeah, so the nice thing about like what I'm doing is, as I mentioned, I'm doing something I'm really passionate about, and what I'm my primary roles are organizing the capital and just bringing in excellent people. Of course, I do quite a bit of marketing. It's like my favorite thing. I love, sharing the story. But as you've mentioned, it really comes down to getting the right people in place. And I think we have a really good eye for what we're looking for, what we need. So I don't think I'm the type of person that, like, I would let my ego get in the way of anything. If some point down the line we need to bring in somebody more experienced and then I can focus on something else, that's totally fine. At the end of the day, I just want to do what's best for the company. I want to do something that, gets to market. I think that's ultimately my goal. So whatever it takes to kind of push to get that, these achievements, that's what I'm going to do.
What's your timeline looking like?
Yeah, I think we have a pretty aggressive timeline as you should. We're looking to generate revenue by 2029. It's aligned with the NRC licensing. We've gotten feedback on our regulatory engagement plan, and if we hit every single mark perfectly, I think it's achievable. Um, I do think some reactor developers kind of get ahead of themselves instead of being more realistic. So of course we have this target. I think based on our trajectory right now, we should be good. But of course, things will probably come up, and we'll just have to remain flexible and adapt to anything that comes our way.
It's definitely ambitious. Yeah, we're building a much larger reactor again in the small modular size up here in Ontario, and if all goes well, I think I have to always revisit this thing, but I think they're aiming for end of 2029, end of 2030 to be grid connected, and I think starting to sell those juicy electrons. So 2029
Yeah,
sounds ambitious. It sounds
it's
ambitious.
very ambitious, but to be fair, I wouldn't have started the company if I wasn't a
If
little
you weren't,
ambitious.
fair enough. Fair enough.
Yeah,
Anything else you wanted to touch on, Sam? The floor is yours.
I really appreciate your content as well. I think what you share with your community is great. I'd recommend anybody interested in learning about Hadron. As Chris has mentioned, we've got a nice website, but you can always reach out to us on LinkedIn. Our team is pretty responsive, and yeah, I happily introduce you to Ross as well.
Wonderful. Okay, well, I look forward to having him on. Okay, Sam, thanks for making the time.
Of course, thank you. That was great. I appreciate it.
Today's episode was made possible through a generous donation from the Xerxes Foundation and from listeners like you making pledges on our Substack. If you'd like to join the tribe, please do head over to our Substack, smash that pledge button, or if you would like a tax-deductible receipt, you can hit the donate button and make a contribution through our fiscal sponsor. We genuinely appreciate your support. It is only through your generosity that we are able to continue to offer energy literacy on demand.